This is part 3 of the videos on simplifying rational expressions. There was some vocabulary defined in the previous videos, so if you're just starting to watch these, you should check out at least the beginning of the first two. We are going to look at adding rational numbers, which are fractions, any number that can be written as a ratio of two whole numbers. We're going to extend that to rational expressions. We'll look at subtracting rational numbers, which is fractions, and then extend that to rational expressions. Let's start by looking at a fraction addition problem. So we have 2/3 plus 1/4 here. And what I'm going to do is draw a picture of this first. So if I wanted to draw a picture of 2/3, I would start with some shape. I'm going to use this rectangle as my whole. And I want to divide that into 3 equal pieces and shade 2 of them. So there's 1/3 and there's my 2/3. And then if I want to add 1/4 in here, let's first start with a drawing of 1/4 so we know how big that is. So let's do it this way. So I'm choosing to draw my quarters going the other way. So there are 4 equal pieces, and I want just one of them shaded. Alright, so if I took this quarter that I have shaded and put it into the empty spot in the other diagram, in the diagram of 2/3, I wouldn't fill it exactly because those pieces aren't the same size. So what I want to do is figure out some way to make these pieces the same size so that I can just combine them into one diagram of the whole. So what I'll do here is in my thirds, in my diagram of 2/3, I will divide that into 4 equal pieces going across. And here in my 1/4, I'll divide that into 3 equal pieces going the other way, going up and down. So now I have 2 diagrams that are each representing some part of the whole, and now my equal sized pieces are 1/12ths. So in this first diagram, I have 8 1/12ths shaded, and I want to add that to my 3/12ths from the bottom diagram. So now that I have equal sized pieces, I can take these 3/12ths that are here and shade them into my diagram up here. So I can see that all together I have 11/12ths. And these were repurposed, so I don't need that diagram anymore. What we did was get a common denominator. And if I was doing this problem without diagrams, what I would do is I would use this idea of a giant 1, which if you're not familiar with, you should really, really, really watch the first video because that's essential to this concept. I would use the idea of a giant 1 and multiply each of these fractions by some version of the number 1 so that I can get them to have the same denominator. So 4/4 and 3/3 are both 1, and multiplying by 1 doesn't change the value. So 4/4 times 2/3 gives me 8/12ths. 1/4 times 3/3 gives me 3/12ths. And then once I have the size of my piece, which is the denominator, I just need to add the numerators. What we'll do on the next slide is look at an example of adding rational expressions, which is a fraction with a polynomial in both the numerator and denominator. Alright, so we've got x plus 2 over x minus 3 plus x minus 8 over x minus 3. The first thing I'm looking for, or I need to know whether my denominators are the same or not. And in this case, I was given 2 rational expressions that have the same denominator, meaning that the size of the pieces is the same. Okay, and so this language about size of pieces is really from our understanding of fractions, rational numbers. But we can extend it to this new, more abstract concept. So I have the same size pieces, which means I can just go ahead and add the numerators. So I'll get x plus 2 plus x minus 8 all over x minus 3. And so I can go ahead and combine like terms, so I get 2x minus 6 over x minus 3. And before I'm done, I always want to think, well, are there any giant ones hiding in this expression? So what I want to do is get both numerator and denominator to be factored completely. And so in the numerator, I notice that both 2x and negative 6 are multiples of 2. And so I can factor out a 2, and I'm left with x minus 3. And my denominator is x minus 3. So here's an opportunity to cancel a giant 1. I can rewrite this as 2 wholes times x minus 3 over x minus 3. And so x minus 3 over x minus 3 is a giant 1. So this just becomes 2 times 1, which is 2. Remember that I can not have any x values that make my original expression undefined, meaning the denominator cannot equal 0. So I can say this original expression is equivalent to 2, except when x is equal to 3. So this is my final answer. We will look in the next example. We'll check it graphically. So I'll show you what that looks like one more time. And if you want more practice with excluded values, check out the first and second videos. All right, I've got x squared plus 8x plus 1 over x minus 2 times x plus 1 plus 2x over x plus 1. So I'm looking at those denominators. They're not the same, but I am noticing that I've got part of a common denominator. So a quick example with rational numbers, if I was doing 3/4 plus 5/12, 5/12 is actually the same as 5 over 3 times 4. And so this helps me realize that I don't need to multiply the denominators together. I can just multiply 3/4 by 3/3 and get my common denominator of 12ths. So 9/12 plus 5/12 is 14/12, which I could then reduce using a giant 1 to 7/6. So that's just a quick example with rational numbers. I'm going to clear that away, but we're going to apply the same concept to this particular problem. So I've already got part of a common denominator. I just need to multiply the second expression by a giant 1, and I'm choosing x minus 2 over x minus 2, so that I get a common denominator of x minus 2 times x plus 1. So I'll rewrite my expressions now. I've got x squared plus 8x plus 1 over x minus 2 times x plus 1 plus the product of 2x and x minus 2 over x minus 2 times x plus 1. So now that I've got my common denominator, I can go ahead and add my numerators. My denominator will stay x minus 2 times x plus 1. So I've got x squared plus 8x plus 1 plus 2x times x minus 2. Now I'm going to want to combine like terms in the numerator because potentially there are giant ones that I can cancel. Before I can do that, I'll need to factor the top. And when we factor quadratic expressions, we always start from standard form. Or we usually start from standard form. So what I'm going to do is multiply or distribute the 2x into the parentheses. So I've got x squared plus 8x plus 1 plus 2x times x is 2x squared. 2x times negative 2 is negative 4x. My denominator stayed the same there. All I was doing was rewriting the numerator into an equivalent version. And now I can combine like terms. So x squared plus 2x squared is 3x squared. 8x minus 4x is 4x. And I've still got my 1 unit. My denominator stayed the same because, again, I was just rewriting the numerator into an equivalent form. Now I can work to factor that quadratic expression. So I've got 3x squared and 1. I'm adding to 4x. I'm multiplying to 3x squared. If you want more practice factoring quadratic expressions, be sure to check out that video. Okay, so I can rewrite my numerator to be x plus 1 times 3x plus 1, and my denominator is still staying the same. But now I'm noticing this giant 1 of x plus 1 over x plus 1. Because everything is written as products, I can go ahead and cancel those out. So I'm left with 3x plus 1 over x minus 2. Remember, as a side note, I was able to do that canceling because I could have written it as x plus 1 over x plus 1 times the expression that I have left, which is 3x plus 1 over x minus 2. Okay, so that this term is a giant 1, and anything multiplied by 1 stays the same. So I've got my final expression here, 3x plus 1 over x minus 2, and those excluded values will be the x values that make the original expression undefined, which would mean the denominator was 0, so x cannot be equal to 2 or negative 1. If I need to, I could always write out that denominator and set it equal to 0 and use the zero product property if just looking at it doesn't work. Alright, so we want to check this now. So what I've done in this next slide is, in orange, I've graphed the outputs for the original expression for every value of x. So I've set it equal to y, and we've got an orange graph there visually showing what output gets mapped to by each input. And then in blue dotted line, I've got the simplified expression. So just from this part of the graph that we can see, they look to be very much the same. So I might want to zoom out and look at that graph in more detail to make sure they don't move away from each other farther out from the origin, but I'm pretty convinced by looking at this that I've simplified correctly. Now I want to check those excluded values. So I've hidden the blue dotted simplified expression, and I'm just looking at this orange line, which represents the outputs for my original expression. So when we check x equals negative 1, we get an output that is undefined, meaning the value of that original expression is undefined when x equals negative 1. And we see that when x equals 2, there's a vertical asymptote there. So the orange line is approaching x equals 2, which is shown here as a green dotted line, but it's never actually going to touch there. So there's also, when x equals 2, the original expression is undefined. Looking at this blue, the simplified expression in function form, when x equals negative 1, y equals 2/3. So that's saying that for x equals negative 1, those two expressions do not have the same value. The original one is undefined and the simplified one is 2/3. We do see, though, that this simplified expression is still undefined when x equals 2, which makes sense because x minus 2 is in the denominator. So we were correct in saying that x squared plus 8x plus 1 over x minus 2 times x plus 1 plus 2x over x plus 1 is equivalent to 3x plus 1 over x minus 2, except when x is equal to negative 1 or 2. So we've got a simplified expression. For every x value, they have the same value, except for negative 1 and positive 2. Alright, let's look at some subtraction now. So starting again with a rational number, which is just a fraction subtraction problem, we are going to run into the same problem if we drew out our diagram, and we're going to need some common denominators here. So I'm going to take 3/4 and multiply it by a giant 1, and I'm going to choose 5 over 5, because 4 and 5, which are my denominators, have no common factors. I'll take 2/5 and multiply it by the giant 1, 4/4. So my new problem, my equivalent expression, is 15/20 minus 8/20. Okay, and now I can, I know that the size of my pieces are 20ths, and if I'm starting with 18 and taking away 8, I will have 7/20 left over. So when we extend this to rational expressions, We'll have to be a little bit more careful with the subtraction, and I'll show you why in a minute. Alright, here we've got an example. The first thing I look at is, are the denominators the same? And in this case they are. So I can keep my denominator, that's the size of my pieces, which are the same, and I can go ahead and combine the numerators. So I've got 5x plus 4 minus, I'm going to put parentheses here, minus 2x plus 16. I put the parentheses there to make sure that I'm subtracting all of the terms in the second numerator. So my numerator is now 5x plus 4 minus 2x and minus 16. Just helped me distribute that negative sign. And particularly when there are already negatives in the second numerator, it's important to use those parentheses. Just keeps everything organized. So 5x minus 2x is 3x, 4 minus 16 is negative 12, and that's over a denominator of 6x plus 3. Let's factor everything to see if there are any giant ones. We've got 3 groups of x minus 4 over 3 groups of 2x plus 1. So I just noticed in the numerator that 3 was a common factor for 3x and negative 12, and 3 was also a common factor for 6x and 3 in the denominator. So I'm seeing a giant 1 here, which I can cancel because multiplying by 1 leaves the value the same. So this is equivalent to x minus 4 over 2x plus 1. X cannot be equal to the values that would make the original denominator equal 0. And to figure that out, I'm going to write it out over here. So 6x plus 3 equals 0. Let's see which values make that true. If I subtract 3 from both sides, I'll have 6x equals negative 3. And then if I divide by 6, I'll get x equals negative 1/2. So my excluded value here is negative 1/2. And there's my final expression. Alright, our last example here is a more complex subtraction example. And so, as always, I'm starting by looking to see if the denominator is the same. In this case, it's not. I am hoping that part of the denominators have factors that are in common, but I can't see it yet because my first denominator isn't factored all the way. So I'm going to start by factoring that x squared minus 9. You can totally do this using an area model, but I'm recognizing the difference of squares pattern here, so I know that this is the same as x plus 3 times x minus 3. And then my second fraction is still the same, 5x over x minus 3. So I was in luck because part of my denominators have factors that are in common, so I'm just going to multiply this second fraction by x plus 3 over x plus 3. I'm running short on space here, but I'll rewrite it below. So my first rational expression remains the same, x plus 6 times x plus 7 over x plus 3 times x minus 3. My second expression now has a denominator that is also x plus 3 times x minus 3, but my numerator is now 5x times x plus 3. So before I subtract here, what I'm going to do is just distribute that 5x. I'm also going to multiply x plus 6 times x plus 7 because I know that I'll want to combine like terms in my numerator. So I've got x squared plus 13x plus 42 from my first numerator. And I've got 5x squared plus 15x from my second numerator. Alright, now I can combine my numerators. So x squared plus 13x plus 42 minus, in parentheses to make sure I subtract all terms, 5x squared plus 15x. The size of my pieces here, so to speak, or my denominator, is x plus 3 times x minus 3. So let's distribute that negative sign, get rid of the parentheses. I'll have minus 5x squared and minus 15x. all over my x plus 3 times x minus 3. So x squared minus 5x squared is negative 4x squared. 13x minus 15x is negative 2x. And my plus 42 stays the same. So there's x plus 3 times x minus 3 in my denominator. And now I want to factor that numerator to see if there are any common factors between the numerator and denominator that I could cancel using a giant one. So actually, before I do this, I'm noticing that all of my terms here in the numerator are multiples of 2. So I'm actually going to factor out a negative 2 because I just prefer to have my x squared term be positive. It is totally not necessary and you will arrive at the same answer, but that just makes me a little bit happier. So this will be negative 2 times 2x squared plus x minus 21 because I factored out a negative number. And now I've got a quadratic expression with a 2x squared, negative 21. I want to add to 1x and multiply to negative 42x squared. The things that multiply to 42 are 1 times 42, 2 times 21, 3 times 14, 4 doesn't multiply in, 5 doesn't multiply in, and then 6 times 7. So I am seeing here that positive 7x and a negative 6x will work. My outside dimensions will be x minus 3 times 2x plus 7. I'm going to need to make a little bit of space here. So what I'm going to do is I am going to erase from the first couple lines that we wrote. And I'll leave space at the very top to write our final simplified expression. And I'll start in a different color just to keep everything clear. So now I'm going up here, and I can rewrite this as negative 2 times x minus 3 times 2x plus 7 over denominator of x minus 3 times x plus 3. I'm seeing a giant 1 or a common factor of x minus 3, so I'm going to cancel those out. And I'll be left with negative 2 times 2x plus 7 over x plus 3. My excluded values are the x values that make the original denominator equal 0, so I cannot have x values of 3 or negative 3. And I should then check this in Desmos by saying y equals the original expression and y equals the simplified expression, just to make sure that those graphs look the same, which verifies that for every x value, the corresponding y value is the same. Or for every input, the value of both of those expressions is the same. We know that it won't be the same at x equals 3 and negative 3, though. We can also check that using Desmos.